In the beginning, there was not light, nor darkness, nor sound. There was only the stage upon which all things would someday appear. An infinite, unseen fabric, stretched in every direction, silent and absolute. Physicists call it spacetime, the deep ocean that carries reality itself. It is not made of matter or energy. But it is the very field in which both are allowed to exist. Every star, every planet, every breath taken by every living thing, is suspended in this invisible sea. Galaxies drift across it like scattered islands. The expansion of the universe is nothing more than the stretching of its surface. And though we cannot touch it, it touches everything. For billions of years, this cosmic fabric has held without faltering. It bends, it ripples, it warps under the weight of suns. But it endures. Even black holes, those dark catastrophes where matter and light are devoured, do not break it. They only fold it into shapes so strange that the human mind can barely follow the curves. Yet there are whispers in physics, calculations and equations that hint at a darker fate. A fracture. A wound in the infinite expanse. Not a meteor strike, not the death of stars, but the breaking of the very stage on which reality stands. If spacetime can shatter, then everything it holds will fall with it. No light. No matter. No time. Ancient myths spoke of worlds ending in fire or ice. But the truth may be stranger. The universe could vanish not with a roar, but in a single, silent heartbeat. For centuries, the cosmos was imagined as a grand theater. A silent, unchanging stage upon which the drama of the universe unfolded. In the mind of Isaac Newton, space was a vast, immovable container. And time a steady, universal pulse, ticking with perfect rhythm from the birth of the world to its end. They were separate, absolute, eternal. It was a comforting picture. Planets traced their orbits in invisible grooves. Stars shimmered from fixed positions. And the laws of motion unfolded with the precision of clockwork. The stage was set, and nothing in the heavens could tilt it. But in the early years of the 20th century, a quiet revolution began in the mind of a man working in a patent office. Albert Einstein dared to ask a forbidden question. What if space and time are not separate at all? What if they are not a stage, but part of the play itself? A living, flexible fabric that bends under the weight of matter and energy? In 1915, Einstein revealed his theory of general relativity. It was more than a new equation. It was the rewriting of reality. Space and time were not rigid, they were interwoven into a single entity, spacetime. Massive objects did not merely sit in this fabric, they curved it. And it was that curvature that told planets how to move, light how to travel, and time itself how to flow. The world needed proof. It came 4 years later, during the solar eclipse of 1919. As the moon blotted out the sun, astronomers measured the apparent positions of distant stars that should have been hidden behind the sun's glare. They were not where Newton's universe would have placed them. Their light had curved, bent along the warped contours of spacetime around the sun. The ancient stage had been overturned. From that moment, humanity understood. We do not simply live in space. We live on spacetime. Every step, every heartbeat, every orbit of every world is etched upon its shifting surface. It is not unbreakable. It is not eternal. It is a fragile, flexible sea. And everything we are is adrift upon it. For all its elegance, Einstein's vision of spacetime carried an unspoken promise. That the cosmic fabric, though pliable, was unbreakable. It could bend, ripple, and stretch. But it would never tear, never dissolve into nothingness. For decades, that promise held. Galaxies drifted, stars ignited and died. And the geometry of the universe unfolded with perfect grace. Yet in the quiet margins of physics, small whispers of doubt began to grow. At the smallest scales imaginable. The Planck length, a trillion times smaller than an atom. Spacetime may not be smooth at all. It could be granular. Like a mosaic made of unimaginably tiny fragments. Shifting and vibrating in a restless quantum dance. These fluctuations, predicted by quantum field theory, are not the gentle ripples of general relativity. They are violent, chaotic. Appearing and vanishing faster than any clock could hope to measure. Here lay the first tension. General relativity's serene curves against quantum mechanics' restless foam. Two great pillars of science. Both proven. Yet fundamentally irreconcilable. Nowhere is this fracture more evident than inside a black hole. At its heart lies the singularity. A region where equations collapse into infinity. Where spacetime's smooth tapestry is crushed into a single, unmeasurable point. Here, the known laws of physics simply stop. It is not merely matter that is destroyed, but the very rules that govern reality. Then came a revelation from Stephen Hawking. Using the mathematics of quantum theory, he found that black holes are not eternal after all. They emit a faint radiation, now known as Hawking radiation. As quantum fluctuations near the event horizon steal away the hole's mass, atom by atom. Given enough time, even the most massive black hole will evaporate entirely, leaving behind nothing. If black holes can fade into emptiness, what does that mean for the fabric that contains them? Could spacetime itself evaporate? Could the stage of the universe one day dissolve back into the quantum chaos from which it emerged? These questions remain unanswered. But in their shadow lies an unsettling truth. Spacetime may not be the eternal stage humanity once believed. It may be a temporary construct. A fragile bridge between the birth of the universe and its eventual silence. And somewhere, far in the future, or perhaps closer than we think, that bridge may begin to crack. For centuries, even as physics transformed, one quiet faith endured. That while the stars may burn out and galaxies may drift apart, the fabric beneath them would endure forever. Spacetime was the foundation. The silent stage on which the universe would endlessly unfold. But then came the calculations. Cold, impersonal lines of mathematics. That spoke of a different fate. One scenario emerged from quantum field theory. A possibility both terrifying and hauntingly simple. False vacuum decay. In this vision, the universe as we know it is not in its most stable state. It sits instead in a delicate, temporary balance. A false vacuum that only pretends to be permanent. If a single point of spacetime were to drop into a lower energy state, it would trigger a chain reaction. A bubble expanding at the speed of light, rewriting the very laws of physics in its wake. Atoms, stars, and the constants that define reality would vanish into a new and alien set of rules. And there would be no warning. No resistance. Only the sudden end of the universe as we know it. Another possibility lay in the early universe. Cosmic strings. Thin, one-dimensional defects in spacetime. Forged in the first fraction of a second after the Big Bang. Infinitely long and impossibly dense. They could slice through the cosmos like razors. Their passing warping spacetime so violently that the fabric itself might unravel. Still more unsettling was the thought of gravitational instabilities. Points in the universe where extreme curvature could fold spacetime back upon itself until it tore. The collapse of massive structures. The collision of black holes. Or the unpredictable dance of quantum gravity. Could, in theory, trigger catastrophic deformations from which the fabric could not recover. These were not the inventions of science fiction. They were the offspring of real mathematics. Tested against the rules that govern reality. And they were not inconsistent. On paper, each scenario could happen. The reaction in the scientific community was mixed. Some resisted. Not out of denial, but because such endings were too final. Too absolute. If the foundation itself could fall, then nothing in the universe was truly safe. Others accepted the possibility with a kind of quiet awe. Physics had always been about uncovering the truth, no matter how unsettling. And so, the idea took root. The understanding that spacetime is not a perfect, untouchable canvas. It is fragile. It can be bent. It can be worn thin. And in rare, extreme conditions, it can break. When it does, there will be no flames. No collapsing sky. No final cry from the cosmos. Only the sudden absence of everything. The theater erased. The lights extinguished. The story of the universe ending mid-sentence. Chapter 5, Listening for the Break, Deeper Investigations. Once the possibility of a cosmic fracture entered the language of physics, it could no longer remain a mere abstraction. If spacetime could fail, then somewhere, somehow, there might be a trace. A faint tremor in the deep ocean of the cosmos. Physicists began to listen. Not for a roar, but for whispers. The first of these ears on the universe were the vast interferometers of LIGO and Virgo. They were designed to detect gravitational waves. Ripples in spacetime born from catastrophic cosmic events, such as the collision of black holes. These waves, passing through Earth, stretch and compress distances by less than the width of a proton. But in that delicate trembling, researchers hoped to see more than the signatures of violence. They looked for distortions that did not fit the patterns predicted by relativity. Asymmetries, echoes, or interference that might hint at the fabric itself beginning to fray. Other eyes turned skyward, toward the oldest light in existence. The cosmic microwave background. It is the faint afterglow of the Big Bang, mapped in exquisite detail by missions like WMAP and Planck. This ancient light carries the fingerprints of the universe's infancy. Subtle variations in temperature. Slight twists in polarization. Minute irregularities in its smoothness. Most align with the predictions of inflationary theory. But here and there, anomalies remain. Unexpected cold spots. Regions of unusual symmetry. And polarization patterns that defy easy explanation. Some suggest these could be the scars of primordial defects. Places where spacetime's birth was less than perfect. Meanwhile, deep beneath the Franco-Swiss border, the Large Hadron Collider pushed matter to its limits. Protons collided at energies not seen since moments after the Big Bang. In the debris, physicists searched for particles or resonances that might betray the presence of extra dimensions, or show deviations from the standard model. Both potential clues to the deeper architecture of spacetime. Occasionally, an anomaly would appear. An unexplained surplus of high-energy photons. Or a fleeting hint of an unknown particle. Most would fade under further scrutiny. But some stubbornly refused to be explained away. And then there were the great voids. Immense regions of space almost entirely empty of galaxies. Stretching hundreds of millions of light-years across. In theory, voids are a natural consequence of cosmic evolution. But a few are so vast, so cleanly cut from the surrounding universe, that they raise unsettling questions. Could these be regions where spacetime's tension is subtly different? Places where the underlying fabric has thinned. Piece by piece, the evidence accumulated. Nothing yet proved that the fabric was breaking. But nothing dismissed it either. Each experiment, each map, each collision of particles seemed to brush against an invisible boundary. A place where known physics grew quiet. And the unknown began to hum. The search continues. Not with the frantic urgency of disaster, But with the steady patience of those listening for a sound, that may take centuries to arrive. Because if spacetime is going to break, it will leave behind signs. Faint, fleeting, and easy to miss. And when it comes, the only warning humanity will ever have may already be echoing in the silence around us. There are endings that come like the slow fading of a candle. A gradual dimming, gentle and predictable. And then there are endings that strike like lightning. Instant, absolute, and without mercy. In the mathematics of quantum field theory, there exists a scenario so stark, so devoid of comfort, that even seasoned physicists hesitate to dwell on it. It begins not with the death of a star, or the collision of galaxies, but with something far smaller. A single, improbable fluctuation. A shift in the energy state of the vacuum itself. If our universe is not in its true, most stable vacuum, then at any moment, one tiny region could fall into a lower energy state. It would be like the snapping of an invisible thread that holds the rules of physics in place. From that point, a bubble would form. An expanding front moving at the speed of light. Its edge an unstoppable wall, where the old laws are erased and replaced with new ones. Inside, atoms would no longer bind. Light might not exist. Time itself could flow in a direction alien to thought. And because this rupture would travel at light speed, there would be no warning. No horizon to see it coming. No time to react. No survivors to tell its story. One instant, the universe would be here. The next, it would be something else. Or perhaps nothing at all. But not all visions of spacetime's death are so sudden. There are quieter dooms. Slower and more insidious. In these, the constants of nature. The speed of light, the strength of gravity. The charge of the electron. Drift by imperceptible fractions over cosmic ages. Stars form under new rules. Atoms decay in unfamiliar ways. The universe remains, but becomes increasingly alien. In the far future, its structure could unravel grain by grain, until spacetime loses its tension, and the last remnants of matter dissolve into a uniform, lifeless sea. Both fates, the sudden and the slow, share a terrible beauty. They speak to the fragility of everything, to the truth that permanence is an illusion. From the moment the Big Bang unfurled the first threads of spacetime, its ending was written into the fabric. And so, the silence grows louder. Not because we can hear the end approaching, but because we now know it must exist. Whether it comes in the blinding instant of a cosmic rupture, or the long twilight of a fading universe, the end is already moving toward us. Perhaps it is still billions of years away. Perhaps it has already begun. The universe has always carried its own death within it, hidden in the mathematics that describe its birth. From the first instant after the Big Bang, every equation of physics has been a double-edged blade. A key to understanding the cosmos. And a reminder that its stability is not guaranteed. For visions rise from the pages of theory. Each one credible. Each one contested. Each one whispering of a different kind of final silence. False vacuum decay. In the quantum view of reality, empty space is never truly empty. It is a restless sea of virtual particles. Its energy defined by what physicists call the vacuum state. If our vacuum is not the absolute lowest energy possible, if it is only metastable, then somewhere, someday, a random quantum fluctuation could push a tiny region into a true vacuum. From that seed, a bubble would expand at the speed of light, rewriting the constants of nature as it swept across the cosmos. Inside its advancing front, the familiar structure of atoms and forces could not exist. It is a doomsday without fire. A transformation without survivors. Mathematically possible. Statistically unlikely. But not impossible. Quantum gravity breakdown. Beneath Einstein's smooth fabric of spacetime. Quantum theory suggests a deeper granularity. A foam of probabilities. Perhaps woven from something more primitive than space or time themselves. In this view, spacetime is not fundamental, but emergent. Like a mirage forming from countless microscopic interactions. Under certain extreme conditions. At densities beyond black hole cores. Or in an expanding universe stretched to its limits. This emergent structure could dissolve. Not torn or ruptured. But simply, gone. As though the scaffolding beneath reality had been quietly removed. Brain collisions. Some theories of string cosmology place our universe as a three-dimensional brain, floating in a higher-dimensional space. Parallel brains, other universes, drift nearby. Invisible but real. If two such brains were ever to collide, the event could unleash energies far greater than the Big Bang, obliterating the spacetime we know. The end would not come from within, but from outside. From the unseen dimensions that cradle our cosmos. Holographic failures. The holographic principle suggests that everything in our three-dimensional universe is encoded on a distant, two-dimensional boundary. A cosmic horizon carrying the ultimate blueprint of reality. If this is true, then our experience of depth, matter, and time is a projection. A perfect illusion maintained by flawless information storage. But perfection is not guaranteed. If that encoding were to fail, through a breakdown in the underlying laws, or a loss of the information itself, the projection could glitch, fracture, or vanish entirely. It would not be the universe collapsing, but the canvas it is painted on, fading to nothing. These are not fantasies. They are born from equations. From experiments probing the quantum vacuum. From the mathematics of higher dimensions. And from attempts to reconcile Einstein's gravity with quantum mechanics. None are proven. All are debated. But each holds the same unsettling truth. That the universe's existence is not inevitable. And that its disappearance could take many shapes. Some ends are sudden, arriving at light speed with no warning. Others are slow, eroding the laws of physics over eons. But in every vision, there is an underlying beauty. A reminder that creation and destruction are two faces of the same cosmic coin. The theories differ. The mathematics disagrees. Yet they converge on one idea. Spacetime is not eternal. And when it ends, so too will everything it has ever held. In the great dark between the stars, the universe keeps its secrets well. Yet, in scattered domes, orbiting stations, and silent underground chambers, humanity has built its eyes, and its ears. Not to look for life. Not to search for worlds. But to ask a far more unsettling question. Is the very stage on which reality plays, beginning to break? The James Webb Space Telescope drifts in the cold stillness of Lagrange Point 2, its gold mirrors unfolded like the petals of a machine-born flower. Every photon it collects has traveled billions of years, carrying an image of the universe when it was young. Webb's mission is not only to peer into the era of the first galaxies, but to measure, precisely, the patterns in that ancient light. Subtle distortions could whisper of new physics, the kind that bends, warps, or tears spacetime itself. On Earth, a different kind of listening takes place. Deep in Louisiana and Washington state, two vast L-shaped corridors stretch across the landscape, each a vacuum tunnel 4 kilometers long. Here, in LIGO's laser-lit silence, mirrors are suspended so delicately they can register a movement smaller than the width of a proton. These detectors do not see light. They hear the faint shudder of spacetime, ripples from colliding black holes, merging neutron stars, or, perhaps, stranger events. If spacetime were to ripple in ways that do not match known physics, it could be a sign that the fabric is fraying. Orbiting high above, the European Space Agency's LISA, Laser Interferometer Space Antenna, has been approved to join the watch. Its trio of spacecraft, separated by millions of kilometers, will listen for gravitational waves at lower frequencies, the deep bass notes of the cosmic symphony. Such signals could reveal phenomena invisible to all other instruments. But watching the large is only half the story. To probe spacetime's deepest nature, scientists must shrink their gaze to the unimaginably small. In climate-controlled rooms, atom interferometers suspend clouds of ultra-cold atoms, letting them drift in freefall. Lasers split and recombine their quantum states, producing interference patterns sensitive to the tiniest distortions in spacetime's geometry. Any unexpected deviation from Einstein's predictions could hint at a breakdown in the smoothness of reality's fabric. Meanwhile, deep beneath the Franco-Swiss border, the Large Hadron Collider continues its high-energy ballet. Protons, accelerated to near light speed, crash together in bursts of pure energy. Most collisions produce showers of particles predicted by the Standard Model. But physicists watch for events that do not fit the pattern, anomalies that might betray hidden dimensions, exotic quantum fields, or even the first artificial trigger of vacuum decay. In dark server rooms, another frontier unfolds, not in steel and glass, but in qubits. Quantum computers, still in their infancy, run simulations that no classical machine could complete in a human lifetime. These models explore the dynamics of spacetime under extreme conditions, the inside of a black hole, the edge of the Planck scale, or the unstable slopes of the vacuum itself. They are experiments of the mind, but their predictions guide the real-world search. From the Chilean deserts to Antarctica's ice, from orbiting observatories to neutrino detectors buried in rock, the network of cosmic vigilance grows. The Planck satellite, before its mission ended, mapped the cosmic microwave background with such precision that it revealed tiny anomalies, regions of unexpected temperature, polarization patterns that defied easy explanation. The upcoming Lightbird mission will push further, seeking the faint curl in the polarization that inflationary theory predicts. Or perhaps, something that does not belong in our current map of reality at all. These tools do not measure fear. They measure truth. They measure the ticking of a clock that has been running since time began. A clock that may be approaching an end its builders cannot yet name. The race is not against disaster. If spacetime were to rupture in a true vacuum decay, no detector could send a warning. The front would travel at light speed, rewriting the laws of physics behind it. By the time any signal arrived, it would already be too late. The race is against ignorance. For in ignorance, the end would come as a silent, final surprise. But in knowledge, however grim, there is a different kind of power. The power to understand one's place in the story of the cosmos. The power to see beauty, even in inevitability. And so, the watch continues. Mirrors hang in perfect darkness. Lasers trace invisible lines through the void. Quantum clouds drift in frozen stillness. Gold petals catch the light of ancient suns. Each instrument listens, not to the stars themselves, but to the fabric in which the stars are stitched. For somewhere in that weave, perhaps in a ripple, perhaps in a map, perhaps in a particle that should not exist, will come the first sign that the universe's foundation is beginning to shift. 9 inches the silent ocean of the cosmos, existence feels immutable. Stars burn for billions of years. Galaxies drift in a slow, stately dance. Time itself seems like the most faithful companion, always flowing forward, always steady. But beneath that stillness lies the possibility of rupture. A fracture not of stone or metal, but of reality itself. Physicists call it spacetime breakdown. Not an explosion. Not a gradual unraveling. But a moment, so brief that the word moment feels too long, when the scaffolding of the universe simply ceases to be. If such a break were to come, it would not arrive like a storm on the horizon. It would be instant. Undetectable until it was already here. Some theories imagine a bubble of altered physics racing outward at the speed of light, a front where the constants of nature themselves are rewritten. Inside this expanding sphere, the rules that allow atoms to hold together, or light to move, or time to pass, no longer apply. One instant, a star burns in the blackness. The next, it is gone, its matter reconfigured into something unrecognizable. There would be no warning. No signal outrunning the front. Even the idea of seeing it happen collapses, because sight itself depends on the physics being erased. Others speculate more surreal endings. What if the speed of light itself faltered, not slowly, but catastrophically, falling to zero everywhere at once? All motion would freeze. Electromagnetic forces would vanish. In the absence of light's heartbeat, chemistry, biology, and thought would end. The universe would become a still life, forever locked in its final frame. Or perhaps time could reverse. From one instant to the next, the arrow of entropy might bend backward. Stars would seem to unburn, collapsing into their younger selves. Galaxies would shrink into embryonic spirals. Worlds would unform, oceans retreating into ancient rain clouds, mountains smoothing into plains. But these reversals would not be experienced as rewind by any observer, because the consciousness observing them would itself be flowing in the opposite direction. It would feel normal, even inevitable, right up until the moment before everything began. Astronomers have tried to imagine what such an event might look like from the outside, if there were an outside to see it from. The night sky might tear like paper pulled apart, the very geometry of space failing to hold. Blackness deeper than any void would seep in, erasing not just objects but the distances between them. In some models, entire galaxies vanish, not by fading into the dark, but by being overwritten instantly by something else. Or nothing at all. Would anything remain? Some theorists suggest that a spacetime collapse could leave behind no debris, no relics, only the absence of structure, a featureless void. Others imagine fragmentary echoes, frozen quantum patterns, shards of information, like the fossilized imprint of a wave that once crossed a shore. And then there is the question that cannot be answered. Would such an ending be felt? Would the last conscious thought be one of recognition? Or would thought itself vanish too quickly for awareness to form? In the face of such possibilities, human instincts strain for meaning. The mind resists the idea of an ending without narrative, a finale without climax. But physics is not obliged to tell stories. If the break comes, it may be silent. It may be swift. And in its passing, there may be nothing, not even memory, to say it was ever here at all. The cosmos would not scream. It would simply stop. 10 inches the deep, ancient quiet of the cosmos. There is no promise carved into the fabric of reality. No vow that spacetime will endure. No guarantee that the rules written into the invisible scaffolding of existence will hold. The galaxies drift, not on the foundation of certainty, but on a trembling sea of probability, a quantum stage whose boards may one day vanish beneath them. If spacetime can end, then permanence is a dream, a shadow we have mistaken for stone. For millennia, humanity has told itself stories of forever. Empires claimed they would stand until the end of time. Stars were imagined as eternal torches. The universe itself was thought to be unbreakable, a vault that could not be breached. But the equations written in the language of physics whisper another story, a colder one. False vacuum decay. Quantum gravity breakdown. Brain collisions. The very failure of reality's own projection. These are not myths, but mathematically possible futures. They carry with them a truth that is difficult to hold. If the stage collapses, there may be no curtain call, no audience to mourn, no archive to remember. Not even the ruins of what once was. For the human mind, such an ending is almost impossible to imagine. Our instincts cling to cycles, to the sunrise that follows night, to the seasons that return without fail, to the idea that life persists, even after death. But a collapse of spacetime is not another winter before spring. It is the end of spring itself. The end of the soil. The end of the ground upon which the idea of seasons could exist. And so, what does it mean, to live in a reality that might not last? It could inspire dread, the kind that freezes thought, as one imagines an unstoppable wave already rolling across the invisible structure of the universe. But perhaps there is another way to see it. Perhaps fragility is not a curse, but a gift. In knowing that nothing is promised, each moment sharpens. The taste of water on a dry tongue. The warm weight of a hand in another's. The brief alignment of sunlight through clouds over a silent ocean. These are not infinite, and because they are not infinite, they blaze more brightly. Humanity, for all its ambition, is not the master of the cosmos. It is a passenger. A flicker of awareness riding on the crest of a wave that has been traveling for 13.8 billion years. A wave that may one day break, and vanish into a stillness so complete that even the word, nothing, would not survive. But perhaps that is the point. Not to outlast the universe. Not to etch our names into a fabric that may one day dissolve. But to live within it, aware that its fragility mirrors our own, and that this shared impermanence is what binds every atom, every thought, every heartbeat into something unrepeatable. In this light, the possible end of spacetime is not merely a story of loss. It is a reminder that we are woven into something rare. That consciousness itself is an improbable bloom on the edge of eternity. And that, even if the loom one day unravels, the fact that it once held shape at all is nothing short of miraculous. The universe does not pause for reflection. Galaxies are born and torn apart without ceremony. Stars ignite and collapse without audience. And yet, here, in this small blue world adrift in a vast black sea, reflection happens. Here, matter has learned to contemplate itself. To wonder. To ask why. And to face the possibility that the answer may vanish before it can be fully spoken. In the end, perhaps the question is not whether the universe will last, but whether we can see its beauty before it changes. Whether, in the slow ticking silence of cosmic time, we can hold this fragile awareness without needing to clutch it forever. One day, the horizon of reality may shatter. The scaffolding of space may fold in on itself. Time may unspool into nothing. Or perhaps, the universe will continue, unaware of the shadows in its equations. For now, the ocean is unbroken. Its surface holds steady beneath the stars. And somewhere in that stillness, a small planet spins. The waves rise and fall. The wind moves over dark waters. For